thumb is for.
Yeah, I put northern one.
Thumb is for RNA. You can double check.
I think northern is RNA.
You can check. You can go Google. You find?
Let's see. Sorry.
I took it right out of the book. Pretty common in northern.
我想想，等到East more.
That's what I want to specialize in, Eastern blotting.
Oh, so you okay?
Dr. Ryan.
Yeah.
Northern blot. RNA.
Okay. Fine.
Yep.
I don't think most of you are. So here is the answer for the lecture 7. Practical application. Most of people use this approach. But sometimes thousands still use it, but it's still open when people do the full cost. They still sometimes, I think they still use solvent to check DNA. So I give you the method. Now you need a Google to search the definition. The first one is Western blot. The second one is a 2D gel electrophoresis, followed by LC mass. You can say mass spectrum. Mass is okay. And the third one is RT-qPCR. Of course, they have many different methods. Okay, we just give you some very common one. Makes sense? And the fourth one, you can say microwave one, or you can say next generation sequencing. You can use either one. But as I said, most times we use next generation sequencing. If you look at the paper, well, most times, I think all the people they use recently a few years, they use next generation sequencing. If you want to publish in Cell Science Literature. The fifth one is PCR. The sixth one you can refer to the question for microwave or next generation sequencing. Okay. That's for practical application 7. Yeah. I hope you understand. It's important because the family exam maybe only have one question, but the integrated step integrate what the method with the practical application. So they integrate them. So which means the family exam will take it from here, but however, will be changed the way it's integrated one research question. It's step by step you figure out. You may use all of the method we use, and also the practical application you have to work on. It makes sense? Is it clear? Okay, I hope you taking my questions. You go back to window again. And for practical application 6, I think most you did it right. Maybe what I want to say one question is B. A, I think only one student she didn't put the answer, so which means maybe you need to refer to other students, or you can ask me, since only for one student. So you can look at that, looking for the answer. And for B, I think maybe some students refer to the answer key from the text. But for B, I think if you think carefully, maybe you need to refer to lecture notes. Because lecture notes give you more clear answer. So basically, you have two cases. One is interpreted glucose, another is absence of glucose. And then, which is your IPT has two cases. And then, which is if you consider glucose, which means you will consider ATP level. That will link with the CRP, CMP protein. It makes sense? That basically can regulate the range. Makes sense? So because the on and off like the protein, if the band, which is if you consider single gene, which means it's on and off. It makes sense? But however, if you add CRP, CMP, which means that can regulate the range or different level. Make sense? So which means now you need to go back to look at the lecture notes and to talk about in the presence of glucose, absence of glucose, how the regulate the system in the B. Is it clear? Okay. Okay. I think most of, I think majority students get it right, but they just partially not right. So if you have a question, you can ask me of class in all class. How many people can follow this? Six. But I welcome you, I encourage you to come to the office, especially when you prepare your slides.
I changed it. I don't know why.
So you understanding and I understanding maybe is kind of different. But of course, I think I understanding is most of them right. This I read one of them. Some people even read a few times and try to understand what it is. Or if you have a question about your presentation, warn you. Also encourage you also warn you. Right? So which is one of your points you get. If you ask me now you point out which side the perfect is. It's not catching the idea. Make sense? What do you have before? How many times have you done that? This is 3 times. One. So which means I give you enough one. So which is not strange. Okay. So as in terms of presentation, we will have first one. Of course, the first presentation is as we already know the points in our so we can give you some idea practice. You know what you should do next. So now we will go to lecture. So I will try to finish it within 30 minutes. That's my lecture. Over the class, start right now. That is for students. Their presentation, after their presentation, we can discuss again. How the paper fit into what we talk about, what's in the future direction. That's fun. So today we will talk about process of transcription. We talk about in different cell types. They have different transcription. Different types. They express different genes. But majority is control, major control. The primary control is by the transcription. Also they can be controlled by translation on the post-transcription process. But the first step is the transcription. Transcription, just a review, basically is a review. It's a very complicated process. But as we know transcription, you may have an idea. They have three steps: initiation, elongation, and termination. One or three steps. But in mammals, the last few years actually, they find another interesting phenomenon called pausing. So, you know here, initiation, I'm talking in terms of pausing. So initiation, they have specific DNA sequence. That is RNA polymerase will bind to this sequence. RNA polymerase. How RNA polymerase bind? RNA polymerase by itself, they don't have strong affinity for DNA. RNA polymerase. They maybe have very weak affinity, but don't have strong affinity for DNA. In other words, which means RNA polymerase will not bind to the DNA. Right? The question how RNA polymerase can bind to DNA, that is by the sequence. So that is the initiation. That is by specific DNA sequence. That sequence can interact with the promoter. Right? So basically what they have is you have one promoter, and then you have DNA sequence. DNA sequence can bind to transcription factor can bind to DNA sequence. And then that will expose. Normally they call active domain. That active domain can interact with the RNA polymerase. Then they can recruit the RNA polymerase to the promoter. Right? That is the initiation. And once the initiation, and then they will go to what we call in protocols. They will go to elongation. Right? So elongation, as you know, because here the jaw is naked DNA. Or in eukaryotes, this cancer cause with that eukaryotes. Eukaryotes is not naked DNA. Right? They have roller block called leukocyte. Right? Also, maybe they have, which means here the structure is a Bijang string structure. Right? So which means they still need an additional factor to remove leukocyte. Right? That's how epigenetic can play a role there. And then they have termination. Termination also have a specific DNA sequence. Right? So in the human genome, we already talk about you have housekeeper gene, right? That normally is active. Make sense? And you have silenced gene, right? Silenced gene you can divide into two categories. One is
SI and MI?
So for you have active gene, right? active gene, right? You can divide a human genome as active gene in terms of gene. And then you, for another gene, silenced gene, one is repressed gene. Repressed. This one is marked by H3K4. I hope that they will talk about. So another is repressed gene. Repressed gene, they can divide as two. One is they didn't talk about that, but one thing they call H3K7. Fuck. Make sense? Another is H3K9, ME3. Fuck. For this category, is most of them that encode development region. So control development. So for this one, control development. And this development region, in the early development, for example, in the embryonic stage, they are silenced. In MIMO, which means at the ES cell, in the blast, communicational blast system, it's in ES cell stage. That is being silenced. Right? Yeah, and then later on, they will turn on. So this kind of gene, actually, they are pulsing. Right? So which means in ES cell, they didn't transcribe the entire gene. However, they have initiation, and then they will pulse there. It's interesting. So they will pause. You may think about that, actually is quite important. What's the development? If you think about it. In terms of development, your cell fate is a rapid change. Right? If you want to rapid change, which means you need to produce protein rapidly. Right? How you can produce rapidly?
mRNA is already there.
So which means that you did a fast transcribe, right? But this gene, in the early stage, they were silent. They were not expressed. What's the way they can do? Which means they have the assemble the entire machinery, the transcribing machinery, at this place, which means once they receive the signal, and then they can immediately start transcribe. Right?
How stable is the RNA that's already been produced?
That produces small RNA, like this sample 100 repeat.
And that's stable enough to last until.
So basically, just like
again.
they just maybe just a travel like this, until they receive the signal for example, the developmental signal, and then they will go, or they could generate a full length of mRNA. Otherwise, they only generate a short fragment of it. So basically, in terms of the transcribing process, you can divide into 4 steps. Right? You have initiation, pulsing, elongation, and termination. Right? How they start initiation? The initiation is determined by specific DNA sequence called promoter. Right? So gene promoter. So it's a specific DNA sequence. Right? So for initiation, so basically they will transcribe at a specific position. So the RNA polymers will transcribe right here is a +1 position. The downstream is plus, upstream is minus. Right? So if you think about, if you want to start a transcribe, which means they will need a position on a polymers at position 1. Right? how to position the RNA polymers, because we just talk about RNA polymers don't have affinity for DNA. Right? So which means that by another sequence element called THTA sequence and the BRE sequence, this one is called co-promoter. So this one actually by protein, that's called transcription factor. So transcription factor, they combine the two here. The transcription factor has they can specifically bind to DNA. We talk about in the prokaryotes. NAC repressor is a transcription factor. They can bind to specific DNA sequence. Make sense? And here is a transcription factor. They can bind to THTA, and then they can recruit. So basically what you have first is THTA, you have protein coming in, binding to here. And then because once a bind, and here they will change the conformation of the transcription factor, which means they will have higher affinity for RNA polymers. Before bind, they don't have high affinity. Make sense? Because before bind, they don't have the conformation are different. Once the bind, which means they can induce the conformation change. Make sense? Which means they will expose the domain they can interact with the RNA polymers. Make sense? And then they will recruit RNA polymers to the promoter. Right? So that is a co-promoter. So basically it's a co-promoter. So here is a co-promoter. And before, upstream of co-promoter, actually they have upstream promoter elements. For eukaryotes, actually here, they have lots of transcription factors. But I don't know, sometimes it works, sometimes it don't work. So here you see these upstream promoter elements that sometimes combine in 10, 20, 30 transcription factors. That will help if you think about it. Because here they go brown. And if you have other transcription factors down here, which means they can either stabilize the RNA polymers that can further increase the affinity. I don't think that they initially want to do just like the practical application. There are another kind of off the compound mechanism to get the response rates, responder concentration. So that's why they have so many transcription factors that can bind into here.
So is the interaction between the promoter and the RNA, is it electrostatic or hydrophobic or?
They use multiple forms.
So just
We can totally call them non-covalent reaction. So they can use non-covalent reaction to stabilize the RNA polymers. There's one thing they can do, right? Another thing, if you think about it, also another mechanism is quite important. Because you have roadblock. What is the roadblock? 硫孔章, right? You have to remove 硫孔章. Make sense? So which means, like here, all the transcription factor, they maybe can interact with the epigenetic factor. We just talked about last week, Monday. So basically, epigenetic factor can change either can remove the 硫孔章. Make sense? Well, they can do that. Right? So like acetylation. So which means like here the transcription factor either can stabilize RNA polymers, or maybe they can recruit the epigenetic factor, influence the 硫孔章stability. Right? and then they can start transcription. Make sense? That's like that. What? Because that is just a basic mechanism. Within, as you know, within the human body, what a gene, for most of the development, there is cell type specific. Make sense? It's cell type specific. Now, different cells, for different cell, they require different express. Well, in some cell type, they will express, in some cell, they will silence. How they control that? They have done by enhancer. I think enhancer we talked about a few days ago, I think a few weeks, 2 or 3 weeks ago. We have one LCR. Some people still remember that? No? That's the LCR. L stands for locus.
Locus control region.
Locus control region. So locus control region is the enhancer. So basically, locus control region is the enhancer. So the enhancer is, as you can see, is up to 50 kb or more. Then we define promoter is very close to the ion polymerase 2. Enhancer is either up to 50 kb more upstream or downstream, or maybe within the gene. It's a very far away. That enhancer will control cell type specific expression. When you do high C, that is called looping. You see 2 peak. So that is enhancer.
So the enhancers just control the structure of the supercoiling, or they are a sequence on the DNA?
That's a good question. So it's enhancer, if you think about this, still by 2 mechanisms. That's a good question. So maybe the enhancer will talk about next slide. The enhancer maybe they can greatly enhance the stability of RNA polymers. Right? Or they can change the nucleotide structure. Make sense? They still by 2 functions. Either increase the ion polymerase activity, ion polymerase, by increase the stability, or change the nucleotide structure.
So they bind to promoters to change the structure.
That's the next slide. So by loop.
So are enhancers like promoters, but they're 50 kilobases more? Are they like promoters, but they're just farther away?
That's a good question. Enhancer most of the time have been transferred.
Okay.
But it's not a promoter.
Okay.
But they have been often transferred enhancer. So how the enhancer can communicate with the promoter? That's by looping. Right? You are far away. So here, the enhancer can form looping, which means here is promoter. So now they can change the RNA polymerase structure. Make sense? Or change the nucleotide structure, or change the chromatin structure at a promoter region. Therefore, they can regulate the transcription. That's the enhancer.
Is the enhancer something you could take out, like just extract it, purify it, and then put it into a different cell, and then that cell changes to that different cell?
Yes, some enhancer can do that. So you take out the enhancer in the different region, actually they can check. They can regulate the gene expression.
Could you do that to change like a blood cell into a stem cell?
No, I think in terms of how to change stem cell, maybe, but stem cell they require a few key factors. Well, because about 4 factors, up to 4 nanometer.
Sucks.
2 and the care with the 4 factors. So basically by looking. So maybe you want, okay, you have enhancer, you have promoter, you want to transcribe a gene. Why one promoter, one iron polymerase is going to travel 2 or 3 genes, only travel 1 gene, only transcribe 1 gene. Well, one iron polymerase only transcribe 1 gene, for example, they only transcribe specific region. They don't go far beyond another gene. Yeah. That is by here is insulator. So basically, insulator can control which region is transcribed. How to do that? That's why the first paper is so difficult, because they will answer you so many questions. That's what we talk about here. Because they look at structure, right? The command structure. Makes sense? So like here, how the insulin work? It's still from looping. Right? So basically they form the looping, and now which they can only go this way, control certain region. So actually with the genome, actually they have lots of looping. The different genes, they have different looping. That looping, but basically they will control specific gene transcription.
So there's always one enhancer for one gene.
One?
There's always just one enhancer for one.
No.
For one off-arm.
Sometimes one gene they have lots of enhancer. But however, it's hard to identify enhancer. Because if you think about it, if 50 kg away, you don't know. Sometimes enhancer is 100 kb away, well, maybe 1 million kb away. So you don't know which gene they control. Make sense? Well, but like recently maybe they have more better idea because now they can use the Hi-C technique to identify specific looping. Well, and then identify specific region, basically the gene, they can group to different region. That will give you some idea. If there is, for example, if they is within this region, maybe you will guess this enhancer control some gene will control some gene within this loop. Because with this loop, you maybe still have quite a few genes.
If you have the insulators that cause the looping, can you have an enhancer within that region that also causes additional looping?
Yes. So basically, sometimes, for example, the looping sometimes like here, like this, and then kind of like this. You can think of it's a structure. They can loop in any way. Depends on how many gene, what gene they control. So basically, by looping them, they will control specific gene. But right now they call looping because they don't know structure. If you think about it. Basically, they have specific structure. Because right now they can only determine this distance. Which means, makes sense? So they have specific structure to control the looping. That's why you have, now maybe you have some big idea now. You have the human genome, it's very, very long. It's very, very long. And you have many, many different genes within one chromosome. Make sense? And then you need to transcribe that they call spatial control, which means spatial temporal control. What means spatial control? We talk about different place. Your gene expression are different. What is temporal? During the development, when in the first cell, and until become the billionth cell, that's control. So which is not a gene control, it's by spatial and temporal control. How that get control? That is by promoter. Of course, you have promoter. Well, you have a combination of promoter, or promoter you have combination of transferring factor. That was we put output was first level control. Makes sense? And then you have enhancer. So which is enhancer that can also control gene in specific region. And after that gene they organize in specific region, normally by looping, by insulin. So now you can control specific gene expression. You cannot mess up. If you mess up, they have big problem. Sometimes we think, just like chemistry, sometimes we don't want to find for the difference. Sometimes you don't need it. Once you ask you something, they say octafold. Octafold is one protein. It's octafold. So how many fold do you think they will produce different effect in terms of protein level? 2-fold? It's small. 5-fold? So within our early development, we have three germ layer, three germ layer. How to control the three germ layer? Octafold, the key rule. So basically, the expression level don't need too much. 1 and 1.2. 1 will go to one germ layer. The cell will become one germ layer. If 1.2, they will become to another germ layer. Sometimes you don't need too much protein. Only 1.24. So which means the concentration is tightly controlled. Make sense? How the tightly control is by combination of enhancer promoter. That will control the chromosome structure. It has what we call enhancer is it's not only one enhancer. Right? How many enhancers control one gene? Within one enhancer, they have many transcription factors. So basically, they can control the binding, control the protein, and also control the amount of protein binding to enhancer promoter. Therefore, they can get it right the mark. Unfortunately, not the project. Because it's something to be out. I think in your practical application 5 or 6, they give you some idea, but that is very simple model. It's an angle model, or like they use the equation called the binding constants equation. Well, to quantify that, called repulsiveness, but in reality, it's much more complicated than that. Another insulin, a very important function, is they can block. Like here, they can block the spread of hydrochromatin. For example, here, you have hydrochromatin, euchromatin. If you have insulin here, actually insulin can block the spreading of hydrochromatin. Any question for me? No? It's one question. Define the functions of promoter, enhancer, and the insulin. discuss and have some students answer.
So I think promoters just change the affinity for RNA polymerase to bind different DNA. Enhancers open up supercoiling. They make loops out of the supercoiling of the chromosome to.
I don't know. I would say facilitate looping. I don't know if they open up.
That's what I meant. Like they make that like accessible. They open up the supercoil. They make a
Do they open up the supercoil?
makes a loop.
It's not opening up the supercoil. I
don't think that's just stones on the. I don't think that because it's the chromatin.
What's the difference between Utah chromatin and heterochromatin?
That's like the supercoil shit. That's with that's the ball and that's the
It's condensed and euchromatin is open.
No, maybe it has the beam string. Because that's the chromatin. The ball and the beam string.
Then what is the heterochromatin?
It's just like a coiled version of that. Yeah, with like X turns per coil or whatever. And then insulators just like pinch off the enhancers, I think.
So, any student want to answer the question? What's the function of enhanced promoter?
Modulates the binding affinity of RNA polymerase.
Let's say it can modulate the binding affinity of polymerase. The other function?
Yeah.
They can change the chromosome structure.
You like that?
No, it just is like color. So like. Yeah.
Okay, I'll take it. You don't need a blue? You're good without blue?
Well, I have a blue.
There's not a name, but then we have like 4 people per group.
Just write group 1. Group 1.
So I think how do you want to enhance? The enhancer is like a promoter, just distant way, distant way of promoter, by one function for single function of the promoter. How about usual? What's the function of usual?
To inhibit the enhancer.
That's kind of function, right? So one of them is enhancer blocker, the other one is to prevent the domain from interacting with another opposing activity.
Good. So you can, which means you can limit. You can limit the enhancer function. Right? Limit the enhancer function. And then prevent spreading helical. Right? So that's the function. So now you will, so you have fixed by port, and you have in your, I think maybe you receive this one. That one you can keep them. You don't need to turn in today, which you can use it for doing the presentation. But start from this week. You don't need to turn in this one. Okay. And then you will turn in this one. Okay. Okay. So once you turn in, I will according to the question you ask plus your limit type and give your extra points. Right? Good. Any question? No? Come to the first one.
You don't sound nice.
No, that's fine.
So you want how voice?
I just need a
So the sound is the sound. What?
You have another USB on the side? Yeah, just need a
What?
Okay, I'll connect it.
Yeah. Okay, let's work on the first book. They will talk about the three-dimensional genome organization in the software.
How's it going? My name is Ryan.
Most
We're going to be talking about three-dimensional folding and functional organizational principles of disability. So to start out, I'm going to talk about some background information, and then we're going to look at the relationship between chromosome conformation and genetic function, followed by how Hi-C can be used to define interactions between active and inactive domains, and finally how a probabilistic model can be made to predict the chromosome content map. So a really common method used to study chromosome folding is chromosome conformation capture, or 3C. This is really good at looking at small-scale chromosome folding, but doesn't do a very good job on a whole genome scale. This is a really common trade-off with a lot of methods where they have really high resolution, but not a very large scope, or they've got a really big scope and can measure the whole genome, but don't have a really high resolution. Real quick, a few terms to know. Biotinylation is the attachment of biotin to a segment of DNA. Ligation is the phosphate ester linkage of two segments of DNA that combine them together. And restriction enzymes are used to cut DNA at a specific set of base pairs. Here's a quick video of high resolution chromosome conformation capture, or Hi-C, which is what they use in our paper.
Proximal Hi-C.
And come here.
What?
Proximal Hi-C.
Oh, sorry.
We start with intact tissue from plants, animals, and human cells, or cultured cells. Chromatin is packaged into three-dimensional structures predicting the relationship between genomic and physical distance. Sequences that are closer on the same chromosome are also closer in physical space. Our method exploits this relationship between linkage and proximity to enable whole chromosome scaffolding in basic genomes. The DNA in the sample is cross-linked in vivo to fix DNA sequences present inside the same cell. Cross-linking tracks sequence interactions across the entire genome and between different chromosomes. Cross-linked DNA is fragmented with endonucleases. Fragmented loci are then biotinolated and ligated, creating chimeric junctions between adjacent sequences. This process is called proximity ligation. The more often two sequences are joined together, the closer these two sequences are in genomic space. Biotinolated junctions are purified and subjected to paired-end sequencing. The proximity ligation rates are then mapped onto a graph assembly. Proximity information is used to assign contigs to chromosomes and order and orient them along chromosome scaffolds. This results in fully scaffolded chromosomes of virtually any size. This process also detects structural variation and corrects assembly misjoins, as well as maps the three-dimensional conformation of chromatin within a population of cells. Bring the power of Hi-C into your lab today. Learn more by visiting phasegenomics.com.
go back.
Good.
Go back to the
Change the
What are the deals?
technology. Over here.
go over it a little more. In this particular experiment, they used the restriction enzyme DPN2. And so what they did is whenever a pair of DNA is interacting and crossing together, the restriction enzyme will cut above and below where the actual interaction is. From there, it's going to be ligated, which will make a loop on the top. And then this cross-linked interaction is associated. We can use the strings to kind of see goes from that step to that step. From there, all the strings of DNA from this entire procedure are going to be paired and sequenced to determine the actual folding structure.
All right, so they prepared the same method that Ryan was talking about, the ligated contigs. They prepared about 360 million contigs of them. They extracted them from the nucleus of the embryonic nucleus of the fruit fly. So they did the high C. So the high C is a high resolution 3C. However, this one has a broader scale and it maps the contact area of the entire genome interacting with another entire genome. So they used a probabilistic model to that depended on the scaling factors. So there are lower scaling factors and higher scaling factors. So they used the fragments, compare the DNA from the fragments they collected locally and globally to previous references from other papers that use 3C and 4C. However, they use smaller scaling factors. The smaller scaling factors enable them to see smaller fragments between other fragments that are in a larger scale. So larger scale factors were flanking the smaller scale factors. So the high C method enabled them to see the smaller fragments and the higher frequency contacts, this is the important part of the DNA. This is where the expression happens. So there was a wider scale of the gene of the contact map. They were able to get a wider map than the previous 3C model. So one of the important questions the paper was asking is what is the relationship between the chromosome conformation and the genetic function? Genes are similar to proteins. They have the sequence of the bases is as important as the conformation. Both the sequence and the conformation play a very important role in determining the function of the gene. And the conformation of the gene is determined by the sequence, and it's not random. It's specific. So the conformation depends on the sequence. And understanding the sequence, both the sequence of the bases and the conformation, helps us understand the entire function of the genome, which includes all the functions related to the DNA. So again, as we talked in the lecture, so the DNA, similar to protein, is divided into domains. Each domain has its own function, and insulators or boundaries divide the genome into several domains that vary from 10 to 500 kilobase pairs. Each domain has its own function and conformation. And again, the two functions of the insulators are to block enhancers from binding to promoters, and the other one is to block other domains that have opposing activity. For example, blocking heterochromatin from folding and preventing the function of the chromatin, which is the expressive part. And insulators, there are several types of insulators. They include proteins, CD190, chromatose, CTCF, and DEEP. So these are all repressors, and we've talked about them over here. And the DNase cover sensitivity, which is a part of DNA that's sensitive to DNase, which is a nuclease, either nuclease or exonuclease. And then the histone mark, this is the lysine 4 trimethylated, so this is the activation methylation. If you guys go back to lecture 9, there's a table. This is the activating part. And the insulator region has about 300 to 800 base pairs. So insulator, there are 4 types, so there are domains in DNA, and there are 4 major classes of these domains determined by the insulated region. So there is the dual domain. This is the intrachromatin, about 60% of the entire genome, and then this does not have available markings except for some repressing markings, and it has very low to non-transcriptional output. And then the active domains, this is associated with the histone marks and escalation, after escalation. So this is the eochromatin. And then the repressive chromatin, this is the polychrome, and is associated with the lysine 27, again mentioned today. And then the other repressive, so there are three classes of repressive chromatin, the null domains and these two domains. And these are their relative sizes. So another important question the paper was asking is, what is the relationship between the long range interaction and activity? So the activity of so active domains interact with each other. They do not interact with inactive domains, and the activity is based on the contact frequency is based on the distance, and it's reversible. It's a reverse relationship. So the higher the distance between domains or regions in the DNA, the lower the contact frequency between them, as you can see. And there is it depends on the distance only. So the interaction between arms, inter-arm interaction and intra-arm interaction depends on the region. So it has the same rate. However, the interchromosomal interaction, this happens between inactive domains. So it's fourfold slower.
So the next thing that the paper really focused on was how can IC define long-range interactions between active and inactive domains. So the first thing we looked at was the folding distinction between these two domains. So like we talked about before, the repressive epigenetic domain consists of null, PCG, and HP1 or centromere. And then the active domain is that K4 trimethylated. So the first thing that they looked at was this graph up here. They looked at intra-domain contact density against genomic distance, and they found a exponential decay for the repressive domain to be negative 0.7, while the active domain was negative 0.85. The significant difference is demonstrating that there's different folding within the active domain compared to the repressive domain. And the researchers linked this to being the reason why is because the histone H1 linker is absent in active domains while it's present in the repressive. And this causes the looping on the active domain to be not as compact, and that's what's activating it and letting it be accessible to binding proteins, unlike the repressive domain, which is going to be more compact. So the researchers then wanted to look at how the folding could promote higher order chromosomal structure, and this can be done through hierarchical building blocks. So they looked at two null domains, and they created this graph here, which is a contact enrichment graph. So this white line in the middle is showing a contact enrichment of 11, which is high positive contact between and inside the two null domains. And this is also demonstrating that it has uniform contact density throughout, and it doesn't matter the genomic distance, because there's some that have over 100 kb. So this data is essentially saying that it can promote hierarchical chromosomal organization by folding genomic regions into physical modules, and this can facilitate those longer-range contacts between domains and not just individual elements within the domain. So the paper then looked at the interchromosomal and intrachromosomal interactions for both the active and repressive. So they did this by analyzing a long-range contact by looking at a global physical cluster of both the active and inactive chromosomal elements. They believed that the clustering would have preferential pairing between active and inactive. So they wanted to test this using a coarse-grained matrix level domain, which is this graph over here. And they clustered the two together, and then each chromosome arm showed that it was mostly active domains. And this also demonstrates that higher order inactive-active folding. So the folding distinction that we saw before helped the scientists, researchers discover that the active was able to reach past its chromosomal territory and interact with other active domains, while the inactive was confined to that chromosomal territory and were no longer able to have interchromosomal interactions. So in this graph, they show the interchromosomal interactions with red being positive, and that's shown between both active and active, and that's a strong interaction, while inactive and inactive contact and active with inactive is either having negative or no contact enrichment at all. So that just showed that the interchromosomal was able to have active but not inactive. And then they also looked at intrachromosomal interactions, which were shown with long-range contact between polyclone repressed domains, and then the active domains also had distant and intrachromosomal contact.
So the next question was, how can a probabilistic model to predict chromosomal contact maps be developed? And so there were methods already previously established, like we talked about 3C, that were supposed to have the same intent, but the difference was that they couldn't be generalized. And what Hi-C does is that it's high resolution, and it operates on a genome-wide basis. And so it basically outputs this deeper analysis that the researchers were able to take. Like they talked about, it provided more information and insight on those interdistances for the DNA fragments. And that is what is needed to explain kind of the multiple levels of interaction. And from here, they were able to formulate and test more hypotheses to apply this overall to the whole genome. Just to kind of reiterate, so first the researchers accounted for heterogeneity in the contact densities, which kind of facilitated their identification of the hierarchical folding patterns. Then they grouped the physical domains into two different groups, active or inactive, based on their intrachromosomal contacts. And previous data kind of explained most of the chromosome folding patterns, but what Hi-C was able to establish was that there were specific long-range chromatin interactions that were apparent that weren't explained in the past. So it kind of, Hi-C added on to what was previously known, and it provided this fundamental chromatin interaction map framework. And the basis of this was this mathematical model that assessed the link between chromatin structure and function. And knowing that link is really important because, as seen from the previous data, chromatin obviously, or chromosomes fold in a complicated heterogeneous regime. And as Dr. Wren has talked about in previous lectures, the structure controls the DNA accessibility, which is determining whether genes are active or not. And all of that depends on the conformation. And so these physical domains kind of serve as the key fundamental chromosome folding units. And if those can be understood, because it's thought of that they're kind of reflected or caused by these underlying epigenetic markers. And so if all these basic principles can be understood, then it can be further applied, which is what the researchers' intent was, just creating this foundation to apply later on. And so, like I said, this foundation was made. They hope that it can be applied into future, more complex topologies to be analyzed. The main importance of their data was that they were able to provide these raw numbers, which could imply statistical significance if needed to help serve as future foundations. And they developed this probabilistic model, which was based on these simple principles of just assessing the link between structure and function. And yeah, in the end, they hope that more complex models can be built off of this to give more insight into how nuclear shape affects overall genome function.
So to summarize, physical domains reflect epigenetic domains, and these epigenetic modifications can have impact on the physical domain and function. Hi-C can be used to observe folding patterns and interchromosomal interactions between active domains. And using global modeling of active and inactive domains, for the identification of long-range interchromosomal interactions, a chromosome contact map can be quantitatively predicted.
I was like, click it.
Right.
Any questions?
So,
So we can open discuss.
any questions?
So basically, all Hi-C is doing is it's separating the domains that are actually physically touching, and then you just sequence them, and then that's what tells you where all these touches are happening.
Well, they use a lot of like math. They use predictions. So they took these pieces and compared them. So locally and globally, meaning that so they have the DNA piece. There is a reference DNA of the entire genome, and they compare the pieces of the DNA in the entire reference genome. So the local is locally meaning you're comparing a small piece of your DNA to the reference. Globally meaning comparing the entire genome. If you compare the entire genome, there's going to be a lot of gaps, because it's not completely matching. But there's the predictions. There's a lot of math in it, and they use a lot of references to predict the smaller, well, not small, but like fragments that were not detected previously.
Okay. But yes, it does measure like where it folds into each other.
And it's just by like the two sequences of two different parts of DNA. It's like, oh, well, these two are together, and then it just infers that. Okay, that's sweet.
It might be outside scope of this paper, but did they mention how DNP3 knew where to cut?
I don't know if it specifically knew where it cut, but I think there's a lot of places where it could cut, is what I'm guessing.
I think the endonucleases are specific, so I think there's like a certain sequence in the RNA. I'm not sure why there is a certain sequence in the RNA where the cells like cut over here. I think.
I'm assuming it was just more of a comment. Cut a lot of places.
So can we use another restriction enzyme to test in this?
I would assume yes.
Well, yeah, like DNAs. Well, it's kind of it degrades DNA. It's an exo and endonuclease, but it's also considered restrictions, I think. But I think, are you asking whether you can cut the DNA with something else that the restrictions are?
No, I mean another restriction enzyme, because in this article they use only one restriction enzyme to cut it. I mean, I'm sure you can always use another restriction enzyme. You just have to see if it's going to be site specific for what you're trying to cut and see. So it doesn't matter what the kind of what restriction enzyme is, right?
I think it's a specific. So the DMP2, maybe the Drosophila, the fruit fly, it's specific. I think that's why they use it.
I'm assuming they're just looking for a restriction enzyme that has enough, where the DNA has enough fragments that are compatible with that it's like really common, so it cuts a lot of places.
They wanted to get fragments, so like they wanted to get fragments that are 800 base pairs. So I think that restriction enzyme cuts them to that size. So maybe they chose it for that reason.
How many chromosomes do flies have?
Well, there was 6, I think.
6? That's what I think too, but I wasn't sure.
I think that there was a figure where they had 8 or 6, something like that.
8 or 6.
Oh.
There's a figure where it had.
I'm just curious.
There it goes.
That's how you.
Now we're cool.
So I think 6 or.
This is 6. I think it's. But you can Google them.
Okay. Just curious.
Any other question?
One more. You mentioned in Maddie, but the different holding active versus inactive domains is
So the holding is different because the active doesn't have the H1 histone anchor in it, so that's cause it changes the nucleosome packaging. So without that, it's not packed as tightly as the WordPress would be. So that's what's helping it become activated, is that it's more like beads on a string and not so much like the 30 nanometer fiber.
So for the inactive interaction, because inactive chromosome is the condensed, right? So how come it interact to each other?
Why they interact?
Yes, because the inactive chromosome is condensed and
Yeah.
confined to the chromosome. So how come two inactive chromosomes?
So they can interact in intrachromosomally, but they can't do an interchromosomal interaction, so they can't expand past that chromosomal territory like the
It has low frequency as well.
yeah, and it's at lower frequency. The two active domains that are doing the interchromosomal contact are at low specificity as well. So they're not as accurate as they could be, but the inactive is just confined to that one domain. So they can interact in there, but no, like not past that.
So you talk about physical domain.
Yeah, domains.
How big is the physical domain?
So like
how
there,
many genes in one domain?
so I think like the insulator regions define the domain, and the size is between 10 to 500 kilobase pair. So I think that's a gene. Is the domain a gene?
No, not so, because I heard quite often is the physical domain. So how you define the physical domain based on contact map? What's the size in the contact map?
Based on the I think based on the frequency and activity. So active domains interact with all the active domains. They don't interact with.
So for example, right now I know, okay, you have one compound is linear. Right? So how you define the physical domain?
Is it from the sequence and also from the activity?
Yeah, because it's like,
Yeah, like the
Yes.
insulator is defining the borders of the domain.
I think that is a very important question. I think, thank you. Maybe I can do one slide.
The activity.
I have 3 minutes to go on and find the paper. And we will find how many of you have a paper in your hands? No? Look here. This one you find information how the linear contact is a very important concept. So if you look here, can you read here? So this roughly is 1/12,000 K. Here is 13,000 K. Which in the between here, lots of pieces. 500 K. How big is 500 K? It's very big, huh? And this region, you can look. In this region, actually, they have two, they organize into two domains. Right? Because this domain, which is the linear region, is more frequently contact. So which is, in other words, is that region is organized, you can draw picture. You have linear, you have this domain, or this one, this is linear, right? So what you can have, so which is here, in this region they can have this, and then maybe like this, and this region like this. And, right. So which is here is one physical domain, here is another physical domain. So which is within one domain, they have lots of G. Make sense? Here. So in here they have lots of G. So which is with this domain, as you can imagine, if they want to contact, of course this frequency is much higher than contact here, right? Because they're in the one confined region and organized. So basically what the idea is in entire this paper, your chromatin is linear, or it's linear, and then you just make it like this, and then like this, like this, and like this, like this. Make sense? And like for example, if they have active one, here is active, here is, so which means maybe here, the two active one maybe will come like this, but it's not continuous, it's not fully merged. It makes sense? And then they can contact here, or here is inactive one, maybe they will continue something like this, one, and here they come like this. It makes sense? And then, so basically that's the domain they call physical domain. And then basically your linear chromatin is separated by that way. Now you maybe have a better idea when we talk about the gene regulation now. If they in this region within here, of course they can, if they have enhancer or have insulin, which means they can regulate in this region. Make sense? Well, there will not, it's not easy to complete. And that's is how in terms of the chromatin folding. Any other questions?
So the insulators, are the insulators proteins and or sequences, or are they the complex?
Insulin is a protein, they combine it. So insulin they come here, they come here. Also within each individual one, like here you know it's 500 kb. With the inside, they also have lots of looping. That is by insulin. So insulin they can outside also come by inside. You know exactly the combination of the protein. Right? Insulin have many different insulin. Right? So hope you can understand this figure. You can put your finger back here. And your then packet here.
Holy shit.
You feel like this here.
There you go.